Hi there, can you see me? Yes, wonderful. All right, let me then go to the screen. And can you see my screen as well? Yeah, all good. Cool. Nice to meet you. Thank you all for being here. My name is, as was stated, Arthur Gassner. I am a software engineer at biped.ai. We just came back from CES. And today we will dive into one of the areas of our software pipeline, namely the ground plane detection. All right, so let's dive in. First, a little bit about myself. As stated, Arthur Gassner, software engineer, biped.ai. I hold a master's degree in robotics from the EPFL, and my main areas of expertise are in machine learning and computer vision. But what is and who is biped.ai? Biped.ai is a Swiss startup. We're building the first AI copilot for the blind and visually impaired. Our technology is a device that you wear on the shoulders, as seen here. It has 3 3D cameras that capture the environment around the user and then tracks, predicts, and identifies the trajectories of the objects surrounding the user. All of this is done in real time and locally on the device. Then we focus on what matters the most, and we feed back that information to the user through 3D audio to guide them. Now the thing is, if we're guiding the user, we need to have a way to figure out where is it safe for him or her to walk. We need to have some kind of ground detection algorithm that can tell us, okay, you can go there, but you cannot go there. For the sake of example, here is the data stream from one of the 3D cameras we have. On the left, you have a grayscale image. On the right, you have a depth image. What we want is some kind of algorithm that for each frame will predict the mask of where the user can walk. To do that, we could use deep learning and have some kind of a semantic segmentation algorithm. But the issue is, as I stated, all of the computation is done offline, online, off the device in real time. And deep learning is usually not, let's say, computationally cheap and power cheap. So we have to find another way to do that. And I will now walk you through how we do it. The way we do it is inspired from my paper called Fast Cylinder and Plane Extraction from Depth Cameras for Visual Odometry. What we do is we take the depth image and then we divide it up into a grid of superpixels. One superpixel is a square-shaped set of pixels. Now what we want to identify are the superpixels that correspond to the ground. And usually the ground is flat. So really what we want is to find out which superpixels have data that is laid out in a plane. So planar superpixels. To find those, what we do first is we look at each superpixel and we discard them if either there is too much depth variation in them or if they have too many invalid pixels in them. Once we have done this, we should end up with superpixels that are roughly planar. But the thing is, this will also keep the door, for instance, or any flat surface really. It will keep the ground and the walls and the ceilings and any flat areas that we'll have on the image. So we need to find a way to aggregate those superpixels together and have regions that will be that's the door region, and you have the floor region, and you have the table region, any flat areas. The way we do this is through region growing. We want to merge similar superpixels together such that they form a region. When I say similar, I mean laid out in roughly the same plane. The way it works is you pick one superpixel, and then you compare it to an adjacent superpixel, and you say, okay, are those two superpixels close enough in terms of planarity? Are they laid out on roughly the same plane? And if they are, yes, cool. You can then merge them together and increase the region. If they're not, then you just skip them. What you end up with is a region where all of the superpixels inside of it are roughly similar. They're all roughly on the same plane, and they're bounded by dissimilar superpixels that are not laid out on the same plane. Now, the next question is, how do we compute this similarity between the superpixels? If we want to find out, okay, are they laid out on the same plane, we need a way of doing this. The way we do it is through PCA. PCA will find the directions that explain the highest variance in the data. If we apply it to a 3D point cloud, we can end up with, we can use the least significant component of the PCA as the plane's normal, because that will be where we have the less variation in the data if the points are laid out in a plane. So now we have the normal of each superpixel, and that gives us the power of comparing them, because we can do the dot product of that normal and figure out how close they are on the plane. For the sake of example, let's look at one frame. We've divided that up into superpixels. The first step is discarding all of the superpixels that are non-planar. That's what we end up with. And then what we want to do is region goring. So for each superpixel, we compute the PCA, we extract the normal vector, and then we compare those normal vectors between the adjacent normal vectors. This yields us 3 regions. The green one here is the floor. I mean, we know it's the floor because we know what the frame is like, but this is the first region, corresponds to the floor. The second region is some pole that was in front of the camera, and the third region is the wall that was on the outer right. Now, how do we differentiate between those 3 regions to know which one is the ground? Well, what we do is we just say that the bottommost region is the ground, because it's usually where the ground is located. And there we go. We have a ground plane detection algorithm that can detect in a rather robust way where the ground is and where we can walk. But the issue with this is it's extremely slow. It's far too slow to be run online and not in real time. So we need to find ways to optimize it. The first thing we do is we profile the code to see if there are bits of it, functions or modules that are used quite often and that make up for a lot of the compute time. And it turns out to be the case. PCA is taking more than half of the compute time. So we want to optimize PCA. The first thing we do is we try to see what is actually computed. When you compute PCA, you take the superpixel, you take all of the pixels within that superpixel, and then you compute for all of those data points, you compute the PCA. We don't actually need all of those data points if they're laid out in roughly the same way. We can subsample randomly those pixels, use less points, and it will hence be less expensive to compute, although it will come at the cost of accuracy. But that's one first step towards a real-time runtime. The next thing is Numpy. Computing the PCA is computing the eigenvalues of the covariance matrix of your points. We use Numpy to do this, and Numpy is this widely used linear algebra library for Python, and one would expect this widely used linear algebra for Python library to be highly optimized and blazingly fast. But the thing is, it also needs to be extremely versatile and to cover a lot of edge cases. So if we look at the computation of the covariance matrix, we see that a lot of checks are done every time you call it. Those checks are there to ensure that the data you feed to the function are actually not one of those edge cases. We know that what the data we're feeding it to the function is not those edge cases. So we know we'll always pass those checks, and hence they're relevant. So we can just not do them, go straight to the computation, and have on top of the random sampling, we have a 3 times boost. So that's good. We went from 0.2 FPS to 0.6 FPS. It's good, but it's not quite yet enough to run in real time. The next trick is to use psytho. What we do first is we identify functions that are very often used, especially in for loops, in the Python code. Then we move them to Python. Python is a superset of Python, where you can also write in a C-like syntax, and that enables you to have a faster runtime. Doing this, so first, here's an example of the such functions. What we do is we select a bunch of functions that are very often time called, we move them to Python, we implement them in Python, and overall this gives us a roughly times 20 runtime boost. And there we go. We went from having nothing to having a ground detection algorithm that works, but is not really real time, to one that we can run in real time on the device locally. And there we go. Thank you for for listening to this talk. To quickly summarize, to detect the ground, what you do is you divide up the space in superpixels. Then you discard all of the superpixels that will not be the ground because they're not planar. And then you compute for each of those superpixels their normal. Then you do region growing and you select the bottommost region as being your ground. To make it faster, you do random subsampling on the PCA, you bypass Numpy checks that you don't actually need, and then you identify and move the frequently called functions to psytho. I would like to thank SwissNex in China, SwissNex in China for inviting me and Biped for this talk, as well as Aman Bansal, who worked on this and whose internal presentation was heavily inspired from for this talk. Thank you. If you have any questions, I'm happy to answer them at the QA session afterwards.